This is Knowledge Engineering with Semantic Web Technologies, Lecture 3, Ontologies and Logic. In this part of the lecture we will talk about inference and reasoning algorithms with description logic. So in the last part of the lecture you have first learned of description logic, that this is a part, or let's say a fraction, of first order logic, and it's a fragment which is decidable instead of the semi-decidability or undecidability of first order logic. So let's have a look again at the general structure of a description logic's knowledge base. So we know we have a T box, which means this is the part of the knowledge base which contains the so-called terminological knowledge, so knowledge about classes. In this case, we call it also concepts of a domain. And we have the A box, which is the assertional knowledge, so the part of the knowledge base which covers knowledge about individuals and entities. In more sophisticated or more complex description logics, you also have an R box which states knowledge about roles, so about properties, which means properties, sub-property relationships, and how more complex roles or properties here are constructed. So usually a knowledge base like that is connected to a kind of inference engine, which means we can draw logical conclusions, inferences over the knowledge which is there in the knowledge base. So what we want to do in this part of the lecture is we want to look at some general inference problems or problems of inference that can be solved with the help of a knowledge base. So what are the typical problems of inference that you want to solve? So imagine you have designed a knowledge base with terminological and assertional knowledge. So the first thing what you want to know, of course, is my knowledge base valid at all? So is the global consistency of my knowledge base secure? So for that you want to know whether you are able to deduce here the bottom element, so which is false, of course, from your knowledge base. So the question is here, does the knowledge base make sense? So this is the most basic thing. Consider the knowledge base does not make sense. Of course, you want to know why. So one of the reasons could be, for example, that your classes are somehow inconsistently defined. So the class inconsistency would be another question. You want to know whether your class is consistent or not. So whether your class here also computes or is equivalent to nothing, which means your class must be empty if it's inconsistent because there is no individual which fulfills the definition of your class. So this is something which should be checked then. So we have general consistency of the knowledge base and class consistency. Another thing what you could ask is, is some class eventually part of another class? So is class inclusion or class subsumption true or false? So you simply ask here about the structure of a knowledge base. Is a class C a subclass of knowledge of the class D? So this would be class inclusion or subsumption what you can ask. If you can ask for subsumption, of course, you also can ask for equivalence. So what we test here is we ask if the class C really is the same than the class D. So of course they can have a different, let's say, definition, or they can be constructed in different ways. Nevertheless, these constructions can be somehow equivalent, and of course we want to test that. So this is now among the knowledge base itself and knowledge about the classes. What else can we ask about classes? So if we compare two classes, C and D, with each other, of course, they can be part of each other. They can be equivalent. Another thing which would be interesting would be, are these two classes disjunct? Which means if I simply look at the conjunction of the both classes, is this conjunction eventually empty? So if this is the case, then I know that the two classes are disjunctive. So there are no individuals which at the same time belong to both classes. So class disjunctiveness is rather important. So this is a lot of things about classes. Of course, then we can also look at the individual level. whether an individual is member of a class. So we ask for class membership, and we simply ask, is the individual A contained in the class C or not? So this would also be something which we are interested in, and whether we can deduce this fact from our given knowledge base. So if we do this for one individual member, maybe we are also in the other way around interested which members are in a specific class. So we want to find all individuals X for which it holds that X is a member of the class C. So this means find all known individuals of class C. Why I'm writing here known, you will see it soon. So this has to do with the so-called open world assumption, which we will deal with in the next part of the lecture, and which is also a property or a distinct property of the description logic. So in class generation, or in this retrieval example, you just try to find out which are all the individuals which are in that class. So this is some kind of class extension rule. So these are the general problems of inference. If we look at our description logics, okay, we know most description logics are a decidable fragment of first-order logic, which means if we want to prove, or if we want to carry out these reasoning tasks, of course we can use a reasoning algorithm which is known already from first-order logic. So just remember, we have talked about the Tableau algorithm for first-order logic, so we can use it. The only thing is, of course, we have to take care a little bit, because these first-order logic inference algorithms, like the Tableau algorithm, they can be used, but they have to be adapted for description logic, simply because these algorithms do not necessarily always stop and deliver a result for a question we have. So we have to keep in mind, also for the next parts of the lecture, that the already known Tableau algorithm has to be adapted, especially for description logics, to guarantee always that it terminates. So, yeah, in the lecture, or in the course of the lecture, of course, we will simplify this a little bit, and we will only then later on look at a Tableau algorithm for the most simplest, deductively complete description logics, which is ALC. So if we are using the Tableau algorithm, for example, to solve our inference problems, our reasoning problems, the problem here in general is the Tableau algorithm shows only the unsatisfiability of a theory, which means the unsatisfiability of a knowledge base. So therefore, our problems that we have seen must be somehow, of course, adapted. So we have to adapt the introduced entailment problems to the detection of contradictions in the knowledge base, because we test for unsatisfiability. So we have to prove the unsatisfiability of the given knowledge base. So this means we have to adapt our problems. Besides the first one simply was, we asked, is a knowledge base consistent or not? So are there inconsistencies and are there contradictions? Then of course we can simply use the Tableau algorithm straight away to find that out. Okay, but we also have to ask about classes, class inclusion and stuff like that. And of course these problems have to be adapted, and I will show you how this will work. So what we are doing now is we're trying to reduce the already mentioned inference problems to unsatisfiability. So first let's look at the class consistency or class inconsistency. How do I prove that? So usually we are considering a knowledge base, and the class of course is part of the knowledge base. So what we can do here is, of course, we have to reverse the entire problem. Therefore, we have to ask if our original knowledge base combined with the class, and here with the instantiated class, is unsatisfiable. Because if we want to check the consistency of a class, and the other way around, we want to check whether a class is inconsistent, means there is no member in the class. So therefore, we simply assume the other way around and say, okay, let's assume there is an individual A which fulfills the class. And now simply I combine this class instantiation with my knowledge base and ask whether this is unsatisfiable. And if this is unsatisfiable, this means that the negation of that problem would be, would hold. So from that contradiction, we are simply turning it around And you see, if we reduce the problem to that, we can simply here check for class inconsistency. So this is pretty straightforward. It's a little bit more difficult for class inclusion or subsumption, because here, if we want to test whether one class is subclass of the other, we have to combine our original knowledge base with the inverse problem. So, for example, here we have to turn it around. So we have to test that C is not a subclass of D, or C is not subsumed by D. And for this, we have to take into account so-called logical equivalencies, because we can, with the help of logical equivalencies, reduce this subsumption, which is something like, for example, or it can be treated like the implication. We will see that later on when we talk about logical equivalences, that this can be reduced to exactly this problem you see here. So usually this subsumption can be reduced to a so-called disjunction. And if I want to check then again the unsatisfiability, I have to turn it around. So from the disjunction comes the negation of a conjunction, and then I simply ask whether, if then, for example, I instantiate this with a new individual, A is unsatisfiable. Yeah. I admit you have to think a little bit about this problem, but this is the simple, let's say, inversion of the original problem. And if you want to check this with the help of the Tableau algorithm or another algorithm that is based on proof by refutation, you have to test a problem that is reduced to unsatisfiability, like that one. Okay, then for class equivalency, this is quite simple, I would say. So we know two classes are equivalent if they are each other subsumed by the other one. So we simply have to test whether C is subsumed by D and D is subsumed by C. And for this, we use the reduction we have just learned about class inclusion and subsumption. So we simply apply this here twice. So this is then class equivalency. On the other hand, we also have class disjunctiveness. So how do we do that? So let's just think a moment with what we should extend our knowledge base to test unsatisfiability. Yeah, simply we say, okay, if two classes are disjunct, there can be no individual which is at the same time member of both of the classes. So what we are doing is simply we combine the knowledge base with the assumption that we have here individual A, which is new, and which is likewise in C as in D, so which is a member of the class C conjunctively combined with the class D. And then we test whether this is unsatisfiable. And if we have shown that this problem is unsatisfiable, so that this doesn't exist, so this leads to a contradiction, then we have proven that the two original classes C and D are definitely disjunct. Class membership. So this is pretty easy. Class membership, simply extend the available knowledge base with a negation so that A is not a member of C. So you extend the knowledge base simply with not C of A. And you show that this is unsatisfiable. If it's unsatisfiable, you have shown that A is a member of class C. And then for instance generation, so find all C which are a member of the class C. Yeah, this is quite easy. So you have for each individual X, you have to do a class membership test like we did just before. And then we can make an extension of a class like that. So we can find all individuals which are member of a class. This might take a while, so this is not necessarily a trivial procedure, but you see it works. And this is the reason, or this is the way how we really then mechanize or compute these reasoning problems with the help of an already known algorithm that is based on the inverse, principle that we show a tautology simply by proving that the negation is a contradiction. So you remember that. So that means inference problems and description logics, if we are using the Tableau algorithm or any similar algorithm that is based on the same assumption, then first we have to adapt all of the reasoning problems we have to the detection of contradictions in a knowledge base. So it means we have to prove the unsatisfiability of a knowledge base. Okay, so these were inference problems in description logics. In the next part of the lecture, we want to talk about some other properties of description logics before we start with a Tableau algorithm with description logic. So in the next part of the lecture, we are talking about the so-called open world assumption. And then you will also know why this has something to do with sheep.